Hello everyone. In this video I am going to demonstrate LC low pass filter. So as you can see here, this is a low pass filter. This is the inductor L and here is the capacitor C. As you can see, L and C. So this is a LC low pass filter. Here you can see this is a 100 ohms current limiting resistor and this is the resistor across the capacitor. So as you can see, this is the basic setup and I am going to see the response of this circuit. So let us look into the circuit diagram. The circuit diagram will be like this: 100 ohms current limiting resistance. Here will be the inductor, here is the capacitor, and here is the load resistor. So we don't know the value of L. This is just an inductor I was having. I just put it here and I am testing the low pass filter. So let us look into the waveforms in the oscilloscope. As you can see, this is the waveform of the oscilloscope. The green pen is the input pen and the yellow pen is the output pen. So if we separate both the pens, let us take the output pen above. So you can see at this frequency, I am at 1 kHz frequency. So you can see at this frequency, whatever signal is coming in is sent out. So there is no attenuation of the frequency. As you can see, there is no attenuation of the frequency. So now I am going to increase this frequency. Let us increase this frequency and we will be observing. So now I am at 2 kHz. There is no attenuation, we can see. The same waveform I am getting. Input and output waveforms are same. You can see. So now I am at 7 kHz. Let us zoom this waveform by one step. You can see there is some attenuation in the waveform. So if I reduce back, around 5 kHz or around 4 kHz, we can say the waveform was good. Or around 2 kHz, the waveform was good. So now when we are increasing the frequency, the attenuation of the waveform is starting. You can see. So let us change the time period again. So now you can see, you can clearly see the attenuation of the waveform. So now I am increasing the frequency. So as I am increasing the frequency, I am at 10 kHz now. You can see the waveform is attenuating. 13 kHz, 14, 15, 16. You can see now at 17 kHz, 16 and 17 kHz, the input wave is square wave, the green pen, and the output wave is the yellow pen. It is a triangular wave. You can see the waveform has changed. The square wave has become a triangular wave. You can see at this frequency the square wave has become triangular wave. Now if we increase further the frequency, 17 kHz, it is tending to become sine wave. So let us increase the time period further. Let us make it 500. You can see it has already become sine wave. You can see it has already become sine wave. So it is sine wave. You can see it is sine wave. So however, the signal is getting attenuated. The output is getting attenuated, but it is a sine wave. You can see, so like this, a square wave is turning into a sine wave. This is because at some frequency, this circuit is becoming an oscillator, self-oscillator. So it is oscillating at some frequency, that is the resonant frequency of this circuit. So at resonant frequency of this circuit, the circuit is oscillating and the square wave input is turning to sine wave output. We are feeding square wave input and we are getting a sine wave at the output. This is happening at the point of resonance. So now we will see some interesting facts in this circuit. So if we look at the input voltage of this circuit, it is 9.20 volts AC. So at the resonance, this voltage will be maximum. At the resonance, this voltage will be maximum. Let us decrease the frequency. You can see the voltage is reducing. You can see if we decrease the frequency, I am at 15 kHz. Let us read the frequency, how much it is. You can see I am at 15 kHz. You can see the voltage is 8 volts. So if we increase, suppose we are increasing, you can see when we are increasing the frequency, the voltage is increasing. And you can see at certain voltage, after certain frequency, the voltage will drop. You can see the voltage starts to drop. You can see 19.20 is at 28 kHz. 27 kilohertz, 26 kilohertz, 25 kilohertz. So at 25 kilohertz, you can see the voltage is 9.21 volts AC. So this is the input voltage at 25 kilohertz. Let us look into the frequency. This is 25 kilohertz. You can see. So at this frequency, I am at resonance. We are at resonance at this frequency. The voltage at the input is highest. So 9.20 volts AC is at 25 kilohertz. So now we know the resonant frequency of this circuit. Now from the resonance we can easily calculate the value of the inductor. And here we can see at resonance we are feeding a square wave and we are getting sine wave at the output. So this is the point of resonance. So at resonance Fc equal to 1 by 2 pi root over Lc. The resonance frequency is 25 kilohertz. So if we calculate this formula, if we break down this formula, we can find the value of the inductor is 10 millihenry. My resonant frequency is 25 kilohertz and my capacitor is 0.1 microfarad. The C is 0.1 microfarad. So I am having L value of 10 millihenry. So that means this coil is of 10 millihenry. This is a 10 millihenry coil. So like this we can find out the value of L at the point of resonance. So what we have learned? We have learned at resonance this input voltage will be maximum and we need to know the frequency, and from that frequency using this formula we can find out the value of L if we don't know the L or if we don't know the C. In my case I don't know the L. I just brought an inductor from the shop and I was testing the LC circuit, LC low pass filter circuit with that inductor, and I came to know my inductor is having an inductance of 10 millihenry. As you can see, this is the view of my inductor. So like this the LC low pass filter works, and at the resonant frequency the square wave input waveform turns into a sine wave waveform. Thanks a lot. Thanks for watching.